I'm Gabrielle. I'm going to be doing homework part 3, part A. So this is the amount of heat added to the system that was removed. That's going to be an isothermic reversible compression of an ideal gas. So the first thing we want to do is we're going to write down the first law of thermodynamics. So the differential amount of change of internal energy equals the differential amount of change of the work done on our system minus the pressure of our external times the differential amount of change of our volume. Okay, so this is a reversible equation. So this means that this is going to be reversible, so our pressure at the external is going to equal our pressure at the internal. And since this is an ideal gas, we can use our ideal gas law. So let's rewrite this. dV. And we also know that our change in our internal energy also equals our CV over dt, which is going to be our heat capacity times the differential amount of change in temperature. We know this is isothermic, so that means there's going to be no change in temperature. So this is going to equal 0. So now we know this is 0. So now let's solve for both sides. So this is going to be dq equals RT over V dV. Okay, we know that RT are going to be constant in this problem, so let's just integrate on both sides. So our dq is going to be from 0 because that's going to be when no heat is added to the system. And then our final pressure is going to be the total amount of heat added to the system. And then this one's going to be our starting volume, so V1, and our starting ending volume, V2. Also to note is that when we're compressing it, our final volume is going to be half the size of our initial volume. So this is going to be, V2 is going to equal V1 over 1/2. Okay, so now let's integrate. So this is going to equal Q, and then RT is going to come out, and then we have ln of V2 minus V1. Or V2 minus V1. Okay, so after we do this integration, we know that we can solve for this is going to be 1/2. So we can plug this in, so it's going to be Q for RT ln of 1/2. And then we know we can flip it so that this becomes 2, and when that happens, that can be just a negative number. Okay, so now we know the amount of heat that's going to be added to the system is going to be the amount of heat that we need to get out of the system, so that our equation is isothermic. So what it is saying that if we look at this, this is the change amount of heat. So the amount of heat that is added to the system minus this is going to be the amount of heat that needs to be removed from the system so that we stay in an isothermic relationship. So that is why it's negative, and this is okay for our equation. So this is our answer for our A, for our isothermic. Okay. Okay, so our next question says that we need a pressure and volume and a pressure and temperature relationship with an adiabatic reversible expansion or compression of an ideal gas. Okay, so let's also write down again our first law of thermodynamics. So the change in internal energy So our change in internal energy equals our change of the heat added to the system, or total change in heat added to the system, pressure of the external times the differential amount of volume. Okay, so now this is an adiabatic. Adiabatic means there's no heat transfer. So that means there's no heat added to the system. So this is going to be 0. And we also know this is reversible. Reversible means our external is going to be equal to our internal pressure. So we can also use our ideal gas in this one as well. So let's continue what we're going to do. Also, let's keep this as our CV over dt. So our heat capacity at the change temperature minus our RT over V is going to equal dV. Okay, so now that we have this, we know that our CV over dt, this is okay that dt is because this is not an isothermic relationship. This is not an isothermic relationship. This is adiabatic. Adiabatic means there's no heat transfer. That does not mean the heat does not change, that our temperature is not going to change. So that is okay. And now, so we look at it, we have our dt and we have our dv. And we know that our temperature and our volume are going to change. So that means that we're going to have a differential equation and we're going to separate our two variables and then we're going to differentiate both of them, or we're going to integrate both of them in respect. So we're going to take our t and we're going to bring it over here. We know our CV is just going to be a constant for dt, and we're going to do the integration of that, and then we're going to have r, and we're going to do the integration of 1 over v dv. Okay, so we're going to start at our initial temperature and our initial volume, and then we're going to end at just a random temperature and a random volume, which is going to be Vt over T2 over V2. No, T2 and V2. Okay. So now let's integrate it. So CV, and then we're going to do ln of T1 over T2. T2 over T1. Okay. And now we're going to keep our R as a constant. Since this is a negative, we can flip the inside of our integral of our ln. So it's going to be ln V1 over V2. Okay, so now that we see that we have both ln's on both sides, and we have two constants, I say we bring the constant over, and when we bring this constant over, we're going to have this in front of our ln, and then we're going to bring it up to the top, and we have that as an exponent, and then we can cancel out our ln's. So let's do that. So it's going to be CV over R equals our ln T2 over T1 ln of V1 over V2. Okay, and then we're going to bring that up, and then we're going to cancel out our ln's. So that is going to equal T2 over V, T2 over V2 over CV over R, V1 over V2. Okay, so what the question is asking is we want a pressure and a volume relationship. So this means that we have a temperature. So we're going to try to cancel out our temperature or replace it. And since this is an ideal gas, we know that our P1, V1 equals R, T1. And then we know this P2, V2, R, T1. And then we can just like solve for, so it's going to be P1, V1 over R. And that goes for 2 as well. So let's write that and put that in. Okay. So let's go right here. Okay, so now I know that our R's are going to cancel out because it's on the bottom and the top. So then it's going to be P1 over P1. And this is going to be just CV over R. This is going to continue being V1 over V2. Okay, so now what we can do is we're going to multiply this, our CV over R of all these variables, and then we're going to move it over, and we're going to move these over to corresponding these, and then we'll see what we get. So it's going to be P2 is CV over R, and then V2. Well, no, we bring over a V2, so that's going to be a V1. And then this is going to be V2 to the first power. So the first power Then we have a R, so we're gonna multiply the 1 times the R. So that's gonna be just CV plus R over R. And this is going to equal our pressure, 1 over CV over R. And this is going to be volume 2. And this is going to be CV plus R over R. Okay, now we know that all of the exponents are being divided by R, so let's raise it to the power of R so that we can cancel it out on both sides. Okay, so the next thing we want to know is, let's look at our enthalpy. Enthalpy equals our change in, well, just our internal energy plus our P. So this is going to be an ideal gas, right? So then we can just solve for our ideal gas and do for our PV. So this is dV plus our RT. Okay, so now that it's in respect to temperature, let's derive it as in respect to temperature. So it's going to be dH over dt, du dt, and it's just going to be plus R. Plus R. So this is going to equal Cp. Cp, and then this is going to be our Cv, which is our heat capacity, plus R. And this is going to be our constant pressure at enthalpy. Okay, so now we know that Cp equals Cv plus R, and we know we have that, so let's just plug it in there. Okay. And since we raised it to the power, let's raise it to the power accordingly. So it's going to be Cv over Cp equals P1 Cv Cp. Okay. So now that we have this, what we're going to want to do is we're going to get our pressure by itself. So let's raise this to the power of 1 over Cv. 1 over Cv. Okay, so this is going to change it to pressure, and this is going to be Cp over Cv. That's going to be temperature. Okay, now let's look at this. Our pressure 2, these are equal to each other. Our just pressure and our volume are changing accordingly. So this is going to be a constant. So these are going to equal a constant. So the relationship between our pressure and our volume is going to be constant. Okay, so then our next relationship is going to be our pressure and our temperature. So we have our volume, and this is also going to just be an ideal gas. So we can just use our ideal gas law. So this is going to be pressure, and since it's a constant, it doesn't matter if we have a 2 here, 1 here, or 4. Really doesn't matter. So we are going to be, this is going to be RT over P, the Cp over Cv, and this is going to equal our constant. That's a constant. So now, let's look at it. R is also going to be a constant. So when we're going to multiply this, we're going to have the exponents of Cv over Cp. This is going to be a constant, so we can move it over to the constant side. So 1 minus, and since this is on the bottom, P is on the bottom, it's going to be just Cp. I'm going to have to subtract. It's going to be 1 minus Cp over Cv, and it's just going to be T is going to be Cp over Cv. And this is going to equal a constant. So now instead of Cp over Cv, let's use one of the variables that is common for the heat capacity ratio, because this is the heat capacity ratio. Let's just use K. It's okay. So we want K out. We don't want T to the K. So we want that to be by itself. So let's raise everything to T to the K to the 1 to the K. So this is going to be P. And so then we move it over to the other side.